This conference will now be recorded.
Hello everyone. So here we have a question that calcium carbide produces acetylene on reaction with water. So this problem is based on synthesis of CC triple bond, that is acetylene, the simplest member, starting from calcium carbide. And that reaction we have already covered in the last class. So we can solve this problem based on that particular synthesis reaction. But here chain of reactions are there. Just see, first it is saying calcium carbide produces acetylene. Now calcium carbide is CaC2, and from 1 mole of CaC2, which if I write the full structure, it will be like this. So from 1 mole of this, there is formation of 1 mole of Hc111CH, which is acetylene. Fine. And next reaction is ethylene can be obtained by reduction of C2H2. So if I do reduction of this acetylene, we can get CH2 double bond CH2. Fine. So ethylene can be obtained by the reduction of C2H2. So this is the second one. Suppose this is the first reaction, which is number A. Then this is number B, which is the second reaction. And C is polythene is produced by polymerization of, sorry, it will be C2H4. C2H4. So this is C2H2. This is C2H4, and if we do polymerization, we will ultimately get polythene. Now this is asking that calculate the theoretical yield of polythene per kilogram of CaC2. Okay, so here we will see per kilogram. That means here the amount is 1 kg for CaC2. Now, if it is 1 kg, if you convert it to gram, it will be 1000 gram. Now, we need the molar mass of CaC2 if we want to calculate the moles. Because when you see, this is already balanced equation, right? So, from 1 mole of this, we are getting 1 mole of C2H2. And from 1 mole of C2H2, we are getting 1 mole of C2H4. So here we will calculate first what is the number of moles of CaC2, but for that we need to calculate its molecular weight or molar mass. So for calcium it is 40, for carbon it is 12, but it is present 2 times, so that is why it is 24. So it will be 64. Okay. Now if it is 64, then we next will calculate what is the molar mass of C2H4. So this is 1 mole, this is also 1 mole, this is also 1. CH2 double bond CH2 C2H4. C2H4 means again 24 for 2 carbon and 4 for 4 hydrogen. So it will be 28 gram. So now we will do the calculation. From 64 gram of CSA2, we are getting 28 gram. So we are calculating theoretical yield, right? So from 1000 gram, it will be 28 divided by 64 multiplied by 1000, and this will be in terms of gram. So the answer will be 437.5 gram. Okay, so look at the options. All the options are given in kg. So that is the reason when we will express it in kg, we have to divide it by 1000. And after doing this, we are getting 4375 kg. Okay. So this will be the correct option. That is, second option will be the correct option. So now we will start the other processes for preparation of alkynes. And once we finish this preparation all the processes for alkynes. Next, we can discuss the physical properties and also the chemical properties. So this is B, because A we have already covered. This is B. And what is B? It is dehydrohalogenation of dihalides. Now under this heading, the first reaction is when the dihalide is of type vicinal dihalide. Now this reaction we have covered, but again I am just brushing up this slide because that is also under the heading of dehydrohalogenation of dihalides. So this is number one, when we have some vicinal dihalides. And vicinal dihalides means when the two halogen, they will be at 1 and 2 position. So in this case, we are hitting with alcoholic KOH. Remember, it is not aqueous KOH, it is alcoholic KOH, because if you, by mistake, if you write it aqueous KOH, it will be substitution reaction, but here it is halogenation, elimination reaction, removal of H and X, but it is not aqueous KOH. In that case, it will be replacement of halogen by OH, but that reaction we are not doing here. So that is, it is alcoholic KOH. Readily eliminates a molecule of HBr, or better you say HX in general, to form vinyl. Okay, let me keep it as vinyl halide, and HBr is should be written as HX because it is in general way we are saying. So you can see here, this is the general way we have written vicinal dihalide. At 1 position and 2 position we have 2 halogen atom. Alcoholic KOH we are using. So there is removal of H and X. So minus HX, and we are getting this. In the next step we are using some strong base. So here it is very important that in the second step you use some strong base that is stronger than KOH. You have to use some base which is stronger than KOH. And why we are doing so? Because now you are removing HX from a molecule where there is CC double bond. Now this CX bond, when you are trying to break, if you compare with the previous CX bond breaking, obviously now this process is difficult because it is doubly bonded carbon. Okay, this carbon has more S character, so this CX bond is more strong, so you have to give more energy. So that is the reason we are using some strong base, not KOH base. And ultimately, there is another removal of HX molecule, and we are getting CC triple bond. So because of presence of X on a doubly bonded carbon atom, it is unreactive molecule. So what is vinyl halide? This is actually vinyl halide. That is the first generated product, that is called vinyl halide, because this group is vinyl group. So it is vinyl halide because of X present on doubly bonded carbon, it is unreactive. So that is the reason, if you want to get good yield, you have to use some strong base which is called sodium amide in liquid ammonia solvent, or it is also called sodamide, where the anion is basically, if you remove the sodium ion, the anion you are left with is NH2 minus, which is called amide ion. Now we will see the actual example, CH3, CHBr, CH2Br. So here it is at 1 and 2 position, dibromopropane. So first we are getting this molecule where still one more halogen is there, and we are using some strong base so that we can get finally CC triple bond. Now you can also do the reaction in a single step by only using NaNH2 in liquid ammonia. So directly you will get this CC triply bonded this compound, that is alkyne, if you only use NaNH2. Next one is again by dehydrohalogenation of dihalides, but now it is a different type of dihalide. It is gem dihalide. Now what is the difference with the previous one? In the previous one, the two halogen atoms at 1 and 2 position, but now they are present on the same carbon. So that is why their name is gem dihalides. The word is basically generated from the Latin word geminus, which means twig. So here the two halogen atoms, they will be present on the same carbon atom, and that is called gem dihalide. Now, if you compare with vicinal dihalides, alkynes can also be formed from gem dihalides, just like vicinal dihalides, by the action of alcoholic KOH followed by the treatment with NaNH2 in liquid ammonia. Or you can directly use NaNH2 in liquid ammonia. Sorry. So here, if we take example, now both the halogen will be present on the same carbon, and here we have some substituents, one hydrogen, two hydrogen we will write, both side there may be any substituent. So first, when we are using KOH in alcohol, there will be removal of one halogen and one H. And next, when you are using NaNH2 in liquid ammonia, now this X and H will be also removed. And finally, you are getting CC triple bond. So for example, we can take CH3C. Suppose we have Br here. Then CH2, CH3. So here also just I'm jumping the steps. If you do these two steps, or you can also do the single step simply using NaNH2 only without using KOH. And what you will get, CH3C triple bond C CH3. So these two hydrogens and these two bromine, that is the net removal if we talk about two bromine atoms, two hydrogen atoms, right? So this is from starting from gem dihalides, how you can get dehydrohalogenation product, that is you are getting alkyne final. C. So after B, next we have C, where we will do dehalogenation of tetrahalides. 4 halogens will be there. So tetrahaloalkanes such as 1122 tetrabromopropane. So propane is 3 carbon, right? Now suppose I am putting here at one position I am putting bromine. Then at 2 position also I am putting 2 more bromine because it is 1122 tetrabromo. And this is CH3, right? And we have H here, CH3, CBr2, CBr2H. We are treating it with zinc dust. Now what will happen? These two Br and these two Br, it will be removed in the form of ZnBr2. And as we are breaking total 4 sigma bonds, and there will be generation of 2 new sigma, sorry, not sigma, 2 new bonds between 2 carbon. So here our product will be C triple bond C CH3. We are getting alkyne and the byproduct is 2 ZnBr2. Basically, if you consider the reagent, it should be also 2 Zn atom required per mole of this 1122 tetrabromopropane. So here we are removing all the halogens. We are not removing any H. So that is why it is dehalogenation only. It is not dehydrohalogenation. The previous name, remember, it is dehydrohalogenation because you are removing one H, one X in each step. But here you are removing, overall, you are removing 2 halogen molecule. Okay, so that is it is dehalogenation of tetrahalides by direct combination of carbon and hydrogen. Acetylene can be prepared when an electric spark is struck between 2 carbon electrodes in an atmosphere of hydrogen. So here, this will be the picture. Here we have hydrogen and this is carbon electrode. So you need, that is we are preparing directly from the 2 elements carbon and hydrogen. So net reaction we can write like this: in presence of electric spark, you will get a C triple bond CH or C2H2. And this is the diagram for this reaction. Kolbe's electrolytic method. Remember, we have already learned this preparation method previously. And here we will also apply it for the synthesis of alkynes. Now, what type of molecule we will start with? We will start with a concentrated solution of sodium or potassium salt of maleic or fumaric acid. Now, maleic or fumaric acid, these two are actually cis and trans relationship. Otherwise, their molecular formula is same. That is, isomeric relationship is there. So this is basically sodium salt of maleic acid or sodium maleate. One form is cis, another form is trans. It doesn't matter whether you have taken cis or trans because their mechanism is important. So if you look at the overall net reaction that is given here, that is the first equation you are seeing here. Sodium maleate, starting from this, you will get maleate ion and 2Na+. sorry, it is not the overall reaction. It is the first step, not overall reaction, because overall reaction you will get alkyne. So what is happening here? Just the cations and anions are separating. Now the anion will go to anode. Sorry, the anion will go to the anode, because we know at anode oxidation will take place. So when there is oxidation, 2 electrons are removed from this, and there will be generation of radical. Now when there is generation of radical, there will be removal of 2 CO2, which is written here in the right hand side. So what is happening here? If I write, it is like this. So there is CH and then CO double bond O dot. Then C double bond O dot, which is single electron. Now here, if you consider these 2 electrons present here, so this here you can break it here. That is homolysis. So this electron and this electron together, it will make a new bond. Now it is triple bond between 2 carbon, and this electron and this electron, it will make double bond between C and O. Ultimately 2 molecules of CO2 generated. So this is the oxidation reaction you are having in at anode electrode. And what is happening at cathode? At cathode we know there is reduction. Now the 2 electrons that are removed in this step, that will be accepted by Na plus, it will be converted to neutral Na. And there is already presence of water. So this water and sodium together can make NaOH. So the net reaction is, ultimately we are, obviously this is our main target molecule, but we are also getting CO2, NaOH, hydrogen as a byproduct. So why these reactions you should know separately, what is happening at anode, what is happening at cathode. Why you should know it? Because suppose you are getting question where it is given that during the preparation of alkyne by coal-based electrolytic method, in which electrode, is it anode or cathode, CO2 is produced. Or it may be asked that which gas is produced at cathode, then your answer is it is hydrogen. So that is why you should know the full mechanism, which product you are getting at which electrode, that you should have clear idea. Then the next method is heating haloforms. This is the general form of haloform molecules, because X may vary. If it is fluorine, it is basically fluorine haloform, you will hardly find. It is mostly Br or iodo. So we can call it bromoform when it is Br, you can call it iodoform when it is iodine. So, but general formula is CHX3. So when you heat haloform, either you take CHBr3 or you take CHI3 with silver powder. So haloforms like chloroform or iodoform, when heated with silver powder, they form acetylene. So see here what is happening. Here we have taken chloroform, or you can call it trichloromethane, but we have taken 2 moles. This is one molecule, this is second molecule. And look how the molecules are drawn here, so that we can understand which bonds are broken, which bonds are formed. Here we are treating these 2 moles with 6 moles of silver, that is the metallic form, and this together it will make 6 AgCl. So 6 Ag and 3 chlorine atoms coming from one molecule of chloroform, another molecule of chloroform, another 3 chlorine. So together it will be 6 AgCl formation, and this is our main product. Similarly, you can start with iodoform. Here instead of AgCl you will get AgI, but this is same. So total A, B, C, D, E, F, total 4 methods, 6 methods we have learned for the preparation of alkynes, right? Physical properties of alkynes. The first 3 members of alkynes, remember the first member is HC triple bond CH. Gradually, if you add carbon, so this is the next member. So the first 3 members are basically ethane, propane, butane. Though butane here I have drawn 2 butane, you can also draw 1 butane, or whatever it is. The first 3 members are basically gaseous. The next 8 members are liquids, and after that from 9th member they will be solid. Now the reason is very clear. This we have already seen in case of alkenes also, that when you move gradually increase the number of carbon, hydrogens are also increased along with carbon, molar mass is increased, and when molar mass is increased, physical state will be converted from gas to liquid to solid. So this is the reason. They are odorless, they are colorless, except the first member, which is acetylene. There is significant smell, which is garlic smell, and that is not for the molecule itself. It happens because of the impurity which is associated with it. And what is this impurity? Basically, the garlic smell is the main source is this phosphine, which is a pH 3, and hydrogen sulfide, which is H2S. But these two molecules, they are inorganic molecules. They are present as impurity, and that is the reason for their smell, not for the acetylene molecule itself. The smell is coming. Melting point and boiling points. The melting points and boiling points of alkynes slightly higher than those of the corresponding alkenes. Now this is probably due to the presence of triple bond having higher number of weakly held pi. If you consider CC double bond, you have just 1 pi 1 sigma, but when there is CC triple bond, you have 2 pi 1 sigma, right? So when there is high number of weakly held pi electrons, increase of pi bonds means what? Increase of pi electrons, and pi electrons are weakly held compared to sigma electrons. So they will produce stronger attractive forces between molecules. Weakly held electrons means what? Their movement is they will be in flowing condition. So when it is so, the stronger attractive forces will be generated. That is, polarity generation will be easier. Polarity generation, when it is easier, when electrons can move from one side to another side, and as a result, what happens when all the electrons are moving to a particular side, there will be generation of accumulation of negative charge, and the side from where they have moved, there will be accumulation of positive charge. So polarity generation will be easier. So this is the reason why they are having higher MPBP compared to alkenes. Alkynes have linear structure, that we know, and that is the reason. Remember in the structure section, probably in the the previous class of the previous day, there we have seen the structure, and we know it is having linear structure, and hence their molecules can be closely packed in crystal lattice compared to those of alkenes and alkanes, because in case of alkene and alkanes the structure is not linear. So close packing is possible if you consider the solid alkynes, because close packing, that question arises only when it is solid, not liquid or gas, right? So for solid alkynes, this will be the explanation why their melting points are high. Solubility. Now, alkyne is also non-polar, just like alkane and alkene. So obviously it will be insoluble in water. You cannot expect solubility. It is not, there is no such polarity. I know that there is loosely held pi electrons, so polarity generation possible, but it's not so strong that it will be soluble in water. But it is having slight solubility in polar solvents, other polar solvents, because water is very polar. Other polar solvent means which is not so polar like water, right? So that is why solubility is slightly, not very high, and readily they dissolve in organic solvents. So if you take some non-polar organic solvents like benzene, CCl4, petroleum ether, so non-polar will prefer non-polar, so that is why they are soluble. Densities of alkynes, like those of alkenes and alkanes, increase as molecular size increases. Now, when molecular size increases, if you consider density as mass by volume, it is true that molar mass increases when you are moving from first member to second member, that is fine, but you can say that volume is also increasing. But the increase of volume and the increase of mass, if you compare, the increase of mass is high compared to the increase of volume. So ultimately what happens, this ratio, if you see numerator and denominator, the chance of increase in the numerator is high compared to the denominator, and that is the reason densities are increasing. But they are all lighter if you compare with water, because their densities, look at the range, 0.69 to 0.77, where for water it is close to 1. So it is compared to water, it is very light. Density is very low. Okay. Chemical properties of alkynes. So after physical properties, if we consider its chemical properties, broad classification, if we consider, you can see A, B, C, D, E, total 5 types. Now under the first type, that is addition, this will be the most broad. So under addition category, we will discuss 4 to 5 reactions. And then we will start the reactions, which is because of its acidic character, which is possible only when you have some terminal alkyne, that is with CC triple bond, there will be some hydrogen attached in the terminal position. Then only this type of reactions are possible. Then the third one is oxidation of CC triple. It is because of the loosely held pi electrons, they can be easily oxidized in presence of some strong oxidizing agents. Then polymerization is possible, just like alkenes you have seen, where we use the alkene as starting, that is as the monomer, and we get some polymer. And the fifth type, which is isomerization. So from one isomer of alkyne, we will get another isomer of alkyne. So now, as we have seen these 5 types, just have a look. Here we will focus first on addition category. So under addition, there will be 4 to 5 reactions. So what is addition? Addition is electrophilic addition reactions like alkenes are possible in alkynes, and that is because of presence of pi electron density. So in CC triple bond, there is 2 pi electrons, and here we are saying that it is addition, but what type of addition? It is electrophilic addition, not nucleophilic addition we are talking about. Now, why we are calling it electrophilic addition? So it is called electrophilic addition because we will use some reagent from which the electrophile will be generated, right? Now, directly the reagent may be containing some positive charge, but that is not necessary. The reagent may be neutral itself, right? But from that reagent, the electrophile will be generated. And this electrophile is attracted to the CC triple bonds pi electron density. And that is the reason we are calling this addition as electrophilic addition. Now, there are certain reagents which you can express as E and Nu. Though here we are interested in this part only, but as you know, whenever you will break any electrophile, whenever you will break any neutral molecule to some positive part or negative positive part, there will be obviously the counterpart which is negative, and that part is actually nucleophile. But that will be added in the second step. The first step is the addition of electrophile, and that is why it is called electrophilic addition. Now, some reagents are capable of adding to this triple bond, leading to the formation of addition product. So here we have CC triple bond, right? And now, suppose in general, I will write the mechanism first. You have ENU. Now, in this ENU, the pi electron density, it will be attracted to this E part. So I can write here some del plus charge and del negative. Why it is del? Because it is not fully broken. The bond between E and Nu is not fully broken. So you cannot put full positive or negative charge. It is partial. Slight charge separation. Now, when it is happening, these double bonds pi electron density, triple bonds pi electron density is attracted towards the E. There will be generation of positive charge over carbon, and another carbon that will be now connected to this E, and this Nu will be left. Now, this step is basically the slow step. The first addition where this E is added, it is slow step, and this is actually the electrophilic attack step. Electrophilic attack step is this one. Now in the second step, this is first step. In the second step, what is happening? Now in the medium, you have the other part of this reagent. Now this nucleophile will attack to this positive part, and ultimately you are getting the overall reaction will be, in general, we can express it like this. And this step is fast. The previous one is slow. This step is fast. Since such reactions are initiated by electrophiles, that is the E part of ENU, and that is the reason we are calling these reactions as electrophilic addition reactions. And the same reason is also applicable for alkenes. Okay. The addition product form depends upon the stability of vinylic carbocation. Now, what is vinylic carbocation? See, vinyl group is CC double bond attached to some other part. So this is actually the vinyl carbocation, or I'm just writing it as vinyl C plus, which means vinyl carbocation. So this vinyl carbocation, what is its stability? That depends on what type of substituents are present with it, right? So depending on this stability of this intermediate, the addition, what type of addition product will be there, that is controlled, because here we are expressing it in general way. Now you can see some ENU example. What type of ENU you can have? So simply H2 molecule, you can consider it as ENU. Though directly if you use H2, the charge separation in H2 is difficult. So in that case, we have to use some other supporting reagent. So directly it is not possible because it is so homonuclear diatomic molecule, right? Now look at some other ENU. HX. Now here polarity generation is easy because we know halogens are more electronegative, so you can easily put del plus charge, del negative charge. Then water. If you write water in this way, this part is one negative part, this part is the positive part, and this will be our electrophile. And then halogen also. This is also just like H2, homonuclear diatomic. But here also charge separation is possible. So see, what are the reagents we can add? Hydrogen addition, then addition of HX, addition of water, that is hydration reaction, then addition of halogen. So these are the possibilities we can have under the addition reaction of alkynes. The first addition reaction we will see is addition of H2. So when it is addition of H2, this is basically hydrogenation, addition of two hydrogen atoms. Now this part will not go into details because remember it is already discussed. That is how H2 is added to CC triple bond, and when H2 is added to CC triple bond, what you are getting? If you add 1 mole of H2, you will be getting 1 mole of alkene. So this reaction we have already studied under the heading of preparation of alkenes, because by this method, which we are discussing under the heading of chemical properties of alkynes, this is actually also the preparation method of alkenes, because here the product is alkene. And we have already learned it that it is possible when we are heating the alkyne, that is a hydrogen in presence of nickel, platinum, palladium catalyst, and actually depending on how many equivalents of H2 you are adding, you can also get alkane. But if you want to stop the reaction at alkene stage only, then also we have some specific reagent. Now it is depends on us what we actually want to prepare. If we want to prepare alkene only, you have to stop the reaction at this point. But if you want to prepare further, if you want to prepare alkane, then another H2 molecule added, and now you are getting alkane. So if your purpose is to produce this alkane, you have to use 1 extra mole of H2. Here these metal surfaces, this will be basically the heterogeneous catalyst, where on the surface of these metals, these two hydrogens that will be first. The hydrogens will be present on the metal surface like this. Though there is bond between two, but this bond will be broken. And then what will happen? This linear CC triple bond, it will come near to this H, and both the H, it will be added from the same side if you are using this type of metal catalyst, right? So it will be cis addition, or better you say syn addition, that is addition from the same side. Now the reduction of alkyne when you do in presence of Lindlar's catalyst, remember this is already done. Then you get cis alkene. Here also both the hydrogens are added from the same side. What is the difference? between Lindlar's catalyst and this original hydrogen in presence of nickel, palladium, platinum. The difference is Lindlar catalyst is controlled reagent, where if you want to arrest the reaction at alkene stage only, if your purpose is to make alkene, that is CC double bond, not the saturated one, then you have to use this Lindlar catalyst, because here it is the catalyst had some poisoning effect is there, and because of that addition of poison, the catalyst activity is decreased compared to the original catalyst, which is hydrogen in presence of this nickel, palladium, platinum. So now it is controlled, its behavior is controlled, so reaction will not proceed to alkane, it will be stopped at alkene position. And if you use sodium in liquid ammonia reagent, that will give you transalkane. So if you want to prepare alkene, specifically Cs, you have to use Lindlar. If you want to make transalkene, you have to use sodium in liquid ammonia. And the mechanism, detailed mechanism of sodium in liquid ammonia, how we are getting transalkene starting from alkyne, that also discussed in detail. So we will not proceed to this anymore, because that will be simply repetition. We will go to the next reaction, which is addition of halogen, or you can call it halogenation. So halogens act to alkynes. First, formation of trans or E12-dihaloalkene by anti-addition, and then it is converted to 1,1,2,2-tetrahaloalkane. So here in general, if I write CC triple bond, you are using, suppose X2 I am writing in general. First there is formation of one CX bond, one pi bond is broken. So this is E or trans 1,2-dihaloalkene. Though here trans I have not drawn it in such a way, because we do not know what reagents, what substituents both side. But it will be, because as it is anti-addition, so both the halogens will be added from the opposite side. So if one halogen is coming from this side, another halogen will be coming from the other side. So that is it, to be E or and trans. Then when you use another, first there is formation of this by anti-addition, and then if you are using another X2, finally there will be tetrahalogen substitution. So this is position 1, this is position 2. Now it is 1,1,2,2 tetrahaloalkanes. During this reaction, the reddish brown color of bromine, that is if your X2 is specifically bromine and you are doing this reaction and you are already reached at this saturation point at this position, what will happen? The color of bromine will be discharged. So this is also a test for we already have seen in case of alkenes. In case of alkene also, when you add bromine, there is 2 bromine atoms attached, you get bromoalkane, and the color of bromine is decolorized. There is a unique color bromine has, which is reddish brown color. But now as bromine is already added, bromine is no longer present as bromine, and the reddish brown color will be discharged. And it is the proof that the molecule, that is organic molecule, is having some unsaturation. It may be triple bond, it may be double bond. So in this way we can distinguish alkynes and also alkenes from alkanes. So if you have some unknown sample, you just want to be confirmed that there is no CC double bond or triple bond, or if you are thinking, if you are in doubt that there may be some unsaturation, you can do this test. And there is instant color change, easily visible instant color change. So this is a very good reaction for this unsaturation test. Actual example, if we want to see, so the mechanism that I have shown, that is for general molecule, but actual example you can see here. Here we have taken paint 1 ine, we are adding 1 equivalent bromine in DCM solvent, dichloromethane, and 1 bromine is coming from one side, another bromine from the other side. So that is why we are getting E12-dibromo paint 1 ine. Again, we have taken pent-1,9, but now instead of one equivalent, we are using two equivalents. So directly, basically first this molecule will be formed. And in the second step, another bromine will be added. So finally, there is formation of 1122 tetrahalo compound. This is tetrabromopentane. Fine. So it is very important to look at the reagent, how many equivalents are added. Suppose it is given in the question that two equivalent added, and you just have to find what is the product. Suppose product is not given, you have to recognize the product. Then just look at the ratio, how many moles of bromine given. After addition of X2 and H2, the third one is addition of HX. Look at the name, it is hydrohalogenation, because you are adding one H and one X. Now HX, it may be HBr, HCl. Now their rate of addition, or you can say order of reactivity, is this, and it is expected because to break the bond between HI and as you are moving to Br to Cl to HF, gradually when you have reached at this point, it will be difficult to break the bond, because here the bond distance is very high, you can easily break this bond. And when if you can break this bond easily, then only the addition of H and halogen can occur easily, right? So that is why the bond energy matters, and that is the reason why the order of reactivity of HX is like this. Alkynes react with two molecules of halogen acid. So because there is two pi bonds. In case of alkene, just you can add maximum one HX. It is 1:1 reaction, but now it is 1:2. Fine. So here we will see one example with methyl CC triple bond Me. Suppose you are adding HCl to this molecule. So what will happen first? First you will get MECH. Sorry, CH I have already written, so it will not be there. Double bond. Now if you are adding another HCl, now when you are adding the first HCl, just try to understand, it is symmetric both sides. So until that point, you don't have to think that whether to add H on left hand side or right hand side, that you don't have to think. But when you are doing the addition of the second HCl molecule, now this one is not symmetric, right? And that depends on in which side more, that is in which side the carbocation will be more stable. So remember the Markovnikov rule, right? Now if you consider this one, when there is addition of the first H, you will get, suppose the H is added here, that is as I have written here, it is CH2, then the positive charge will be here. And that is actually happening. The positive charge is here and you are adding one more Cl. But another possibility is there, if the H is added to the other side. Now this is the positive charge here. Now if you are thinking that the first one should be unstable because chlorine is present, but remember chlorine is also can have some donating property here, plus. So when it is donating here, there is positive charge over chlorine, but double bond formation between C and Cl, that is another possibility. So because of that, these carbocation ultimately win over the other, and you will get product which will be from this carbocation, that is the first one. So this is the explanation. So until this point there is no problem, but after that, that question arises. Now this thing we have not discussed in the previous two reactions, because in the previous two reactions your reagent is symmetrical, it is either X2 or H2. But now your reagent is HX, it is different, it is not symmetric reagent. So that is why we are discussing Markovnikov. So here the reaction we have done with a symmetrical alkyne, but it may be asymmetric alkyne also. See, if we take asymmetric alkyne example, now the example will be something like this. right? And if you are adding the halogen, that is HX, suppose I have taken HBr. Now from the initial position it is not symmetric both sides. So you have to understand whether to apply Markovnikov or not. But don't follow simply Markovnikov. As I have said, always try to understand whether the carbocation is stable or not. And for that you have to draw the carbocation. If you can imagine it, it is fine. But if you are having trouble, just draw the two possible carbocations and try to understand which one will be more stable. So in this case, after that is when we are adding the first mole of HBr, the first product we will get is the H will be added to the left hand side carbon. That is, to this carbon H will be added, and we will get CBr, and this part there is no change, it is still CH2Me. So it means that the positive charge is generated in this way on this carbon. Now it is expected because here we will have some plus I effect from this side, so that is why this positive charge is stable here. So this through this carbocation you will get the product, and this is according to Markovnikov. Another HBr addition is possible. Now there is two possible generation of carbocation. Now if you are thinking that the carbocation will be generated on the first doubly bonded carbon, it is not right. It will be basically generated in the second one, though halogen is present, but still it can stabilize this positive charge over carbon by donating electron. So that effect we have to consider rather than minus I effect. Plus R effect is dominating. So it will be ultimately when you are adding the second one more H is added. So ultimately it will become CH3. CH2, CH3 or CH2N. So this will be the final product. So see, in both cases, one point is interesting. In both cases, we are getting geminal compound, dihal, isn't it? Because geminal means where both the halogen are on the same carbon. So just like the alkene, anti-Markovnikov addition also possible. If you are adding HBr, you know anti-Markovnikov is applicable only for HBr. So anti-Markovnikov addition is possible when you have some unsymmetrical alkyne. So it has to be any terminal alkyne only. So it is possible if you are doing this reaction in presence of some peroxide, then only anti-Markovnikov possible. And only HBr works for this anti-Markovnikov addition to terminal alkyne. And when it is happening and you are getting double bond, that is, if you just consider the first alkene, both E and Z, both these are possible. So suppose you are doing the reaction in presence of some peroxide, and in general, if you have taken any terminal like this, and you are adding HBr in presence of peroxide, look at the addition. Now, normally what is happening, when you have taken some unsymmetrical, you are adding HBr, the Br is added to that side where you have some R group, but now it will be opposite. Now Br will be added to that carbon where R is not present. So it will be reverse. And here both sisters will be produced. So here this Br and R, if I write R and H like this, so they are opposite. So you can call it it is E. And if R and B are on the same side, you can call it Z. Though further another HBr also you can add. I'm just saying if you are considering this product, if it is only 1 mole of HBr, you are adding in presence of peroxide. Now bromine is added to the opposite side where carbocation is, that is carbocation mechanism is no longer applicable here, that we know. In presence of peroxide it is radical mechanism. So anti-Markovnikov we are getting. And one more interesting point, suppose you are doing this reaction, suppose you have taken acetylene, you are passing that is dilute HCl at 338 Kelvin in presence of Ag2 plus ion as catalyst, then the reaction will stop at vinyl chloride. So vinyl chloride is where the first HCl is added. That means it will stop at alkene stage. It will not move to the alkane. So CC double bond stage, the reaction will be arrested. So if you want to make if your purpose is to make alkene, you can do this reaction in presence of Ag2 plus, so that you can get CC double bond product. Next, we'll see addition of hypohalous acid. So you can directly use HOX or you can use mixture of halogen and water, because these two reagents together, it will basically produce HOX. So alkynes undergo electrophilic addition reaction with hypohalous acid, HOX in general. So you can take, for example, if your X is Cl, it may be hypochlorous acid. If it is Br, it is hyperbromous acid. So unlike alkene, where addition takes place only once with this reagent. Remember in the previous case also what we have seen. Two times reaction is happening. So here also, if you take alkene and if you are doing the reaction with HOX, only one time will be the reaction. But in case of alkynes, addition occurs twice, and that is also according to Markovnikov rule. And the question of Markovnikov arises only when it is unsymmetrical alkyne. Otherwise, the question does not arise. So first, let us take some simple alkyne. Suppose you have taken this one, you are doing the reaction in presence of HOCl. So we don't have to think about Markovnikov because it is symmetrical. So Cl and OH added. Now when you are adding the next HOCl, now the question of Markovnikov arises. Now which side the positive charge will be stable? Remember in this HOCl, what is the positive part and what is the negative part? We know HO and Cl. So HO part, that will be the negative part and this will be the positive part because oxygen is more electronegative, right? Now the negative part will be added to that carbon, as we know, well, lesser number of hydrogen. But here that theory you cannot apply directly because both sides you have same number of hydrogen. Now the question is in which side the positive charge is that will be generated, that will be more stable. Now if I consider this Cl, this is actually the electrophile. Now if this Cl is added, suppose it is added here, so positive charge should be generated at the other carbon and OH is still there. This is one possibility. Another possibility is, suppose I am writing plus, minor, major, whatever. Another possibility is H. Now positive charge is here. And Cl is added here. This. Let me check once. CH. Sorry, the double bond will not be there. Fine. So just compare the two positive charge. In the first positive charge, which is close to OH, here, though oxygen is electronegative, but this type of lone pair, when it will be donated, there will be double bond between carbon and oxygen and positive charge over oxygen. And that is actually make the octet complete, and that is why this type of carbocation will be stable. Though here also this is possible, but it will be better in case of OH, and that is why this carbocation will give more preference, and as a result, if it is so, ultimately when you are adding the next HOCl, this will be the product. So OH will be added to that carbon where the original OH is present. Okay, but remember, when single carbon is containing two OH group, what happens? This type of molecules become very unstable. So this molecule is actually very unstable, and ultimately what happens? This OH bond is broken. There is C double bond O, and this OH is removed. So it is basically net removal of one H and one OH, and ultimately this molecule being unstable, one water molecule is removed. So you are ultimately getting C double bond OH. So this is aldehyde. Chlorine substitution is there, but it is aldehyde. So two times Markovnikov addition is happening based on which carbocation is more stable. And after that, there is removal of water molecule. Now, if I do the same thing with the unsymmetrical, then what will happen? Suppose we have MEC triple bond CH. Now when you are adding the first HOCl, you have to consider Markovnikov, unlike the previous situation where in the first step that question does not arise. Now here Me, so positive charge will be more stable to the left hand side carbon where it is close to methyl group, so that is why it will be like this. Then ClH. Now we are adding the second HOCl, and when there will be again the same thing, which will be added to the carbon where originally which is present, and also here methyl group can also have some plus I effect. So CH, Cl, another Cl. But remember, as we have said, when OH group present, two OH group present in the same carbon, this type of OH bond will be broken. C double bond O. This OH is removed, so it is net removal of one water molecule. So ultimately, you are getting MeCO CHCl2, which is nothing but keto compound, right? So in this case, we have taken only one side, there is some alkyl group. But suppose you have taken both sides some alkyl group, same group or non-same, whatever it is. Now from both sides, what will happen? Two types of ketone can be generated. One water molecule is removed from the final addition product and it will produce carbonyl compound. It can be aldehyde or it can be ketone. So we have seen how aldehyde is generated when it is terminal. This type of alkyne we have taken, and here because of presence of this alkyl group we have MEC double bond O. So this is ketone, and there is also chlorine substitution at the alpha position. Now here one more thing also, just try to notice addition of. Okay, so today we will not proceed to any other reaction because we are already at the end of the session. Next, we will also discuss how water molecule is added. So until now, we have seen total addition of H2, addition of X2, then addition of HX, addition of HOX. All these four we have covered. Next, we will also see how H2O molecules are. So that will be the fifth type of reaction. After four, that will be fifth type. Fine. So we will end the session here. Thank you for listening.